Hey everyone, this is Dr. Walker. Let's look at example number 1 from v586 on the integral form of Faraday's law. This example talks about the electric field induced in a loop. We saw this exact same picture in the lecture notes, and I did ask you to think about why the electric field was going counterclockwise. So let's go over that first. So the reason the electric field is going counterclockwise is because that's the direction of the induced current. So to find the direction of the induced current, we are going to write down that the external field is going into the page. And I had said that the field was increasing into the page, so the change in flux is increasing. So the induced field is going to be in the opposite direction as the external field. And so the induced current is going to have to produce a field out of the page, which means that your fingers, using right hand rule number 3, are curling counterclockwise. So the induced current and hence the induced electric field are going counterclockwise. In this example, we want to figure out what is the magnitude of this induced electric field inside a loop of radius r when the magnetic field changes with time. So let's go ahead and write down Faraday's law. We're going to have the line integral of E dot ds equals the negative derivative of the flux with respect to time, the magnetic flux. So let's go ahead and pick our loop. It says a radius r, so we can pick a loop here. That is going to be our loop along which we integrate. And so we know that the electric field is tangent to this loop at any point, so it's tangent to the little elements ds. So with E and ds being parallel, that means that the dot product vanishes, and we know that E is also constant around this loop because of it's the same distance from that central point, from the center. So this becomes E times the length of the path, which is just a circumference 2 pi r. And then the right-hand side, we're going to write the change in flux as the derivative with respect to time of B times A. We know that the cosine vanishes because the field is perpendicular to the loop. So the field is parallel to the normal to the loop. So the cosine vanishes. We have our maximum flux BA. And we can further simplify here. We know that the area doesn't change with time. The area is going to be pi r squared. We don't have to take the derivative of that, but we do have the derivative of the field with respect to time. And now we can just go ahead and solve for E. All we have to do is divide by 2 pi r. So when we do that, we're going to get E. We're going to get one of the r cancels, the pi cancels, get negative r over 2 times the derivative of B with respect to t. So if we have a problem where we know how the field changes with time, then we can figure out what is the electric field induced. And we're going to do just that in the next example.